All right, let's dive right in. We're heading deep into the world of prime numbers, where two of the biggest, most famous unsolved problems have kept their secrets locked away for centuries. But, a recent breakthrough has just uncovered this shocking clue. A clue that suggests these two mysteries might be connected in a way that nobody, and I mean nobody, ever saw coming.
So just imagine this for a second. What if two of math's biggest, baddest, unsolved problems were actually two sides of the very same coin? What if the key to finally cracking one of these legendary mysteries was actually hiding, in plain sight, right inside the other one? It honestly sounds like something straight out of a detective novel, right? But some brand new, fascinating research suggests it might just be true. So on one side, you've got the twin prime conjecture, and on the other, the Goldbach conjecture. Now, both of these they're deceptively simple. You could explain them to a middle schooler, no problem. And yet, they have stumped the absolute greatest minds in mathematics for literally centuries. And until right now, pretty much everyone has seen them as two completely separate, monumental challenges.
Okay, first up, let's talk about the twin prime conjecture. It's all about these prime numbers that are just two apart, like 3 and 5 or 17 and 19. We keep finding them as we look at bigger and bigger and bigger numbers. But the ultimate question, the one that keeps mathematicians up at night, is this. Is there an infinite number of them, or do they eventually just stop?
And then you've got Goldbach's conjecture. This one says you can take any even number bigger than 2, let's say 28, and write it as the sum of two primes. For 28, that's easy. It's 5 plus 23. Now get this, computers have checked this for numbers all the way up to 4 quintillion without finding a single one that fails. But here's the catch. In mathematics, checking a billion or even a quintillion examples is not a proof. You have to prove it works for every single number forever. And that's the really hard part.
So, for centuries, these two massive problems have been studied on completely parallel tracks. No overlap. But that all changed when a mathematician named Michel Yamagishi decided to look at the Goldbach conjecture through a completely new, fresh lens.
The idea he had is so simple, it's beautiful. First, you just pick an even number, something like 16. Then, you find all the ways you can write it as a sum of two primes. For 16, that's 3 plus 13, and it's also 5 plus 11. Okay, now you just ask a simple question. What's the smallest prime number that shows up in any of those pairs? Well, for 16, it's 3. That's it. That little number is what we're going to call the minimal Goldbach prime.
Okay, now here's where the real genius comes in. Yamagishi built this special kind of mathematical tool. Now, technically, it's called a polynomial, but you can just think of it like an accounting machine. Its one and only job is to go through all the even numbers up to some limit we set and just keep a tally, a running count, of every single minimal Goldbach prime it finds along the way.
So what comes out of this machine is just a set of numbers, which are called coefficients. Each coefficient is just a final count for a specific prime. So for example, the coefficient we'll call C3 is the grand total of how many even numbers have 3 as their minimal prime. C5 is the total for the prime number 5, and so on. It's like a really precise census, and for the very first time, this gives us a way to count these things systematically.
So, with this powerful new tool in hand, it was time to start decoding the results. What kind of story would these numbers tell? What secrets, what patterns were hiding inside this totally new way of looking at the Goldbach conjecture?
The first result that came out was interesting, but it wasn't exactly shocking. The formula for C3, our count for the prime 3, turned out to be directly related to the classic prime counting function. That's a really famous function in math that basically just estimates how many primes there are up to a certain number. So this made sense. It fit right in with what mathematicians already knew. No surprises yet. But this is where the story takes a huge, sharp turn. If C3 was connected to the regular, old prime counting function, what hidden structure was the next one, C5, going to expose? Well, the answer was something that literally nobody saw coming.
And boom, the answer was absolutely shocking. Buried inside the formula for C5 was a completely different function, a function called pi2. Now, this function has nothing to do with adding primes together. Its one and only job is to count how many pairs of twin primes exist. This was the clue. It appeared out of nowhere. It had absolutely no business being there. A property of prime addition from Goldbach was somehow inextricably linked to a property of prime gaps from the twin prime conjecture.
This wasn't just some random clue. This was a blueprint. With this discovery, it was suddenly possible to build a direct, explicit bridge connecting these two mathematical giants that had stood apart for centuries.
So how do we actually build this bridge? Well, the logic is it's just beautifully straightforward.
If you add up all the individual counts from our machine, the count for 3, the count for 5, for 7, and so on, the grand total has to equal the total number of even numbers you started with, right? It's a basic accounting principle. All the parts have to add up to the whole.
Okay, so we know the new formulas for C3 and C5. We can just kind of lump all the others for primes 7 and up into a single group we'll just call H of n, or the rest. Now all we have to do is plug our shocking discovery right into this simple equation.
And after you just move some terms around, you get this, an exact unambiguous equation. Let's just take a second to really appreciate what we're looking at here. On the left side you have pi2, the function that only counts twin primes. And on the right side you have a collection of terms that all come directly from our analysis of the Goldbach problem. This is it. This is the bridge. It's a formal mathematical Rosetta Stone that translates the language of one ancient mystery into the language of the other.
Now, it is absolutely critical to understand this identity doesn't prove either conjecture, but its importance cannot be overstated. It fundamentally changes how we see these problems.
So the key takeaway here is that we now have a direct, exact formula that links the world of twin primes to the world of Goldbach. They aren't just similar puzzles anymore. We know now they are structurally, mathematically intertwined. So think of this identity as a powerful new tool. It really is like finding a Rosetta Stone, allowing mathematicians to use clues and patterns from one problem to finally learn about the other for the very first time.
And that just leaves us with one final, absolutely tantalizing question. For centuries, mathematicians have been trying to climb these two mountains separately. This discovery suggests that maybe, just maybe, there's a hidden path connecting them all along. Could the key to the final ascent up one peak only be possible by first exploring the landscape of the other? We don't know the answer yet, but the search just got a whole lot more interesting.